All right, thank you, Luc, and thank you for the organizers for this opportunity to come and present my work. So yeah, today I wanna talk about some recent work that me and collaborators I want to mention. So Nicolas Mokus here is my PhD student, and I'm going to talk about his work in the second part of my talk. And in the first part, I'll talk about some observational work we've done with Alison Cahoot and Letty Roach. But it's all related to the marginal I zone, and I'm bringing that up here because I think a lot of people have their idea of what the marginal I zone is, but a lot of people have different definitions for it as well, and there is no clear way of properly defining a marginal I zone, which can be troubling because if you think about the dynamic of the sea ice cover overall and the marginal I zone to be the margin, therefore some kind of boundary conditions for the sea ice cover, then we know that if you solve differential equations, the importance of boundary conditions is very important. And so maybe we need to find a way to better understand some of these patterns and dynamics that governs the marginal I zone. So just to go back to the basics here, marginal I zones really is the margin of the sea ice cover. Okay, so very roughly it covers scales from tens to hundreds of kilometers, and you can think of it as kind of the interfacial regions between the open ocean and the pack ice inside, and it kind of looks like that. I mean, for some people, for me, it kind of looks like that, but it can look a lot differently as well. So, for example, in winter when the ice is forming, and then you have a wave field, then you have these pancake ice which are forming, and you can think of that as well as being one of the possible representation of the marginal I zone. One thing that there is agreement though is that ocean waves are an important process, but it's one of many. And there's a lot of different processes, which I'm sure at some points we're going to talk about in the discussion section. But ocean waves and the way they interact with the ice cover is definitely an important one. And that's what I'm going to be focusing on today. And so we can think about this coupled ocean wave sea ice system here as, first of all, looking at the effects of the waves on the ice. And one of them will be that the ocean waves propagate through the ice cover, and they cause the ice to strain in response to the point where it might break, and therefore it forms flows. Or smaller flows in this case, but there are other processes as well caused by the waves, which will push the ice around, cause some collisions, possibly the ice flows to raft on top of one another, and that could be something important as well because that affects the size of the flows in the marginal I zone. But also the effects of the ice on the waves is important. So typically it's been kind of categorized in two different types, okay, but these are very broad categories, and we can go into much more details about what is in each of these categories. But one of them is what we would refer to as the scattering. So waves, essentially, they interact with the flows and they get bounced, or redirected, I should say, in different directions, but without energy loss. So that's the scattering, so energy preserving process. And then you have an array of a bunch of different energy dissipating processes. So overwash would be one of them. So when the waves are washing over the ice, you have friction at the bottom of the ice, and also some energy loss due to the momentum transfer from the waves to the ice, which then collides into each other. And really, we can look at these two here separately, but it's just one. It's just one system which is fully coupled, because the way the ice affects the wave will end up affecting the way the waves affect the ice, and therefore this needs to be considered together. All right, so there we go. So two themes here: how does the sea ice affect the waves, and how do waves affect the sea ice? And I'm going to break it down a little bit further into some interesting questions. Or challenges that are still very much open questions here. And so in terms of the first one is what processes control the observed ocean wave decay into the marginalizer. And I'm going to get back to that a little bit later. And also talking about, this decay, then, can we quantify how quickly the waves decay into the marginalizer? So that's another question. And looking at the effects of the waves on the ice, then we can wonder under which conditions the waves will end up breaking the ice, but also what is the resulting flow size distribution. So that's a very important it's like functions we're interested in. Okay, that's the size distribution of the ice flows into the marginalizer. And so today I'm mainly going to talk about these two questions here. So how fast do wave decays? And I'm going to do that using observations. And the second one is how do the waves affect the flow size distributions? And the main motivation here is that at some point, we would like to develop some kind of parameterizations to couple large-scale ocean wave systems, models like WaveWatch, for example, to a sea ice module in a couple climate models. And for that, we need to understand how the two interact. Okay, so the first question I'm going to address here is how fast do waves decay in the marginalizer? And we have some observations dating back from the 1970s, 80s, which have shown quite clearly that waves decay exponentially, which is great, and that is consistent with the linear theory of wave propagation as well. So that is quite reassuring. But the second thing that was found, and there is a bit less understanding on what's happening there, is that what we call the attenuation coefficients, this parameter alpha here in the exponential decay, seems to depend on the period of the wave, so its frequency, which is very sensible, of course. You imagine very short waves, high frequency waves will attenuate very quickly compared to the very long swell, which will propagate much further in. But it's pretty unclear how the ice conditions affect the way the attenuation coefficient depends on wave frequency. And that's until recently where there's been more observations done, which seems to show fairly consistently that there is some kind of power law relationships between the attenuation coefficients and the wave period, or the frequency, if you want it. It also works. And the question is, of course, is what is this parameter beta here? And there's this nice study here by Melan et al., in which Luc was involved as well, back in 2018, that found essentially by looking at multiple data sets that this power parameter coefficients here is roughly between 2 and 4. And I know Mike is convinced that it is exactly 3. Although I'm a bit skeptical of that. The thing is, if you look at models, there's a lot more variability depending on the model you use. So here, what I'm talking about when I'm talking about viscoelastic layer models, so these are type of models which models the whole sea ice cover as a homogeneous continuum material, so viscoelastic material, and depending on the processes or the rheology, I guess, you put into these models, then you can get a wide range of different power law decay laws between 2 and 11. And there's also the scattering models, which resolves how the waves are scattered by the ice, and these are much higher coefficients. So there seems to be a disconnect here between the theory and the observations. So one question is very important is how does this power law relationships here between the attenuation coefficients of the waves and the wave period emerges from the underlying processes governing this attenuation. And that's a hard question, and I don't think we are close to having an answer to that. But the one I'm going to address today is how this power coefficient beta here depends on the state of the wave ice system. And there hasn't been much done on that. So let's see what we've done. And so here we've analyzed some in situ data, which were collected by by my colleagues Alison and Letty during the Piper's experimental program back in 2017 in the Ross Sea. And they deployed a bunch of wave buoys on top of ice floes to measure the waves. Now, in addition to analyzing that, we also look at the effect of ice concentrations. And so we got some data on that. We also looked at the state of the sea state in the open ocean, so not in the ice, which can be obtained through model outputs. And we also look at wind data, which is something that hasn't really been considered before, and we wanted to see if we could see some kind of effect. So here is the experiment, the Piper's experiment, which was done during the ice growth season in 2017, and there were 14 wave buoys deployed in the Ross Sea. And these were done in two groups. So there were 4 buoys here released, with what we call the west deployment, and that's when the ship went down into the ice. And there were 10 more buoys released as the ship went, like a few weeks later, when the ship went back out of the ice. And so we're going to analyze those differently because they really were done in different locations and measure different things. So the interesting thing here in that particular program is that there was a wide range of ice conditions during these observation periods. There were some ice advance events and also some ice retreat events, and a lot of changes. It's a very dynamic period here. So one issue we had was the waves, the incident waves were not recorded. So we had an issue about the angle at which the waves are propagating into the ice, but we found a way to address that. And just to highlight here the range of ice conditions that we had. So these are 3 pictures that were taken during the programs, where you can see you have these sort of small ice flows, middle-sized ice flows, and then some nearly continuous ice as well. And you can see there is this sort of buoys which sits here on the ice. So that's one of the wave buoys. Okay, so we just recently got a paper on that, and I'm not, you can read the details in the paper, but here's some of the main findings. So we analyze the attenuation data and look at the impact of a bunch of different physical drivers. And we found that ice concentration, mean wave period, and wind direction seem to be very important controlling factor of this power law relationship between alpha and so the attenuation coefficients of the waves and the wave period. And more particularly, we found that at low concentration, beta was close to 3, and for high concentration, it was about 2 or even less than 2. And also, we found that for when the mean wave period was less than 14 seconds, it was also about 3, and for greater than 14 seconds, it was also less than 2. So there is this kind of a parallel here between the concentration and the mean wave periods, which I'm going to get back to in a second. But we also found that actually the wind direction plays an important role here, because it does not affect the power of the relationship here, beta, but it affects the coefficient C in front. So how much waves are attenuating, and particularly on the southerly wind, so waves attenuate faster, so alpha is higher than on the northerly wind conditions. TM is the mean wave period, yes, yeah. So it's average over the whole wave spectrum, yeah. Right, so like I said, we have this relationship here, it seems like, between low concentration and low mean wave periods. So we wanted to see, the extent to which these are correlated. And so we just did a scatter plot, and it seems like, so that's all the east deployment data. So that's the data we got when we had the 10 wave buoys when the ship went out. And it seems like there are two distinct groups here, okay, roughly speaking. So there's one here for low concentration, low wave period, and sort of high concentration, high wave periods. But even more interestingly, when we added the contribution from the second experiment, the West experiment, there we go, it seems to fill the gap right in the middle. And so we can add here even a third group or third regime if you want, okay? But since, you know, these were taken in different locations at different times, so we can separate them quite neatly. And so now if we can look at these three regimes here and try to see if we can find some interesting patterns. And that's what we've done. So here we actually plot the relationship between the attenuation coefficients and the wave period. So this alpha against T, okay? And on a log-log scale, there is at least a section where it looks kind of linear, which suggests a power law. It's not perfect, especially for high wave periods where there's a lot of noise here in the data. So we can sort of get rid of that and just focus on a smaller range of periods. But so like I mentioned before, what we find is, you know, the wind direction plays a role. So you can see when the wind is southerly dominant, so it seems like the attenuation coefficient is shifted up consistently in all three regimes. Okay, so we can now try to summarize these findings here for the three regimes. And don't worry too much about all these numbers, but what's in these three regimes, the power beta here of the relationship is what's important. And it seems we have, so it is about 3 in regime 1, about 2 in regime 2, and less than 2 in regime 3. And if you think about, you know, what these regimes actually correspond to, so we also looked at other metrics here, like the significant wave height and the distance to the ice edge in these three regimes. And we find that this regime 1 corresponds to a region which is close to the ice edge, where there was a lot of wave activity, very large waves, while regime 2 and regime 3 are deeper into the ice covers, with regime 3 being much deeper, with low wave activity. Right, so here the emergent dynamics that we observe here is that ice concentration and mean wave period seems to be important factors here, drivers of the attenuation of waves, and we identified 3 regimes. Low concentration, short, intense waves, mid concentration and mean periods, and high concentration and long waves. And these seem to indicate different laws in the relationship between the attenuation coefficient and the wave period. And also we found a relationship here between the wind direction, but not in terms of the power law, but in terms of the magnitude of the attenuation coefficients. Some things that we didn't consider, but needs to be looked at definitely at some point, is the effect of seasonality. So here, all the data we got was during the ice growth season. You know, during ice decay, do we see different things when the ice is older and more established? And also the effect of other properties of the ice, such as the thickness and the flow size, which could be, of course, very important. And so again, here is the paper, if you want to have a look at it. And talking about flow size, so let me now just try to quickly address the second question I mentioned at the start here: how do waves control the flow size distributions? And let me first briefly talk about what is the flow size distribution, or FSD, and simply defined as the probability density function of the flow size L in a given sample. And the way it is obtained is usually by analyzing aerial images of the ice cover, and then there is work to identify each individual ice flows here. And then measuring a corresponding size for them. There are different ways of doing that, but you can then plot essentially the corresponding distribution of sizes. And since early measurement of that in the 1980s, most of the studies that have done that seems to have shown that there is some kind of power law relationships or a variation of it. Like here we have a break of the slope here, so there could be 2 power law relationships, but you know, governing the flow size distributions. So is it again a power law that we have here? Well, there is this nice paper here by Stern in 2018 that looked at a bunch of different observations, and they found that there's a wide range of powers which were observed depending on the data. And of course, this depends as well on the scale. So you can see here they look at very small scale, so order 1 meter to all the way to over 10 kilometers. So what about the theory? Can we explain this power law? And as it turns out, yes, it can kind of be explained by looking at some fairly simple scale invariant process. So if you take like simple rectangular geometry here, and you consistently break it down into equal pieces, okay, then the corresponding distributions that you have will be some kind of power law relationship. That's just the scale invariance property. But if you do that, the power of the relationship is between 0 and 2. So it seems to be consistent. Although when I saw that, when it was first suggested, there's always something that kind of bothered me here, is that why would, these ice flows always neatly break into equal pieces? But, if you do that, it seems to work. So just briefly now, showing some work we've done recently with my PhD student, Nico Mokus, like I mentioned at the start, where we wanted to see, well, if we simulate the repeated breakup of an ice sheet under wave action, what kind of flow size distribution do we get? And so we took a fairly simple model of, so based on linear water wave theory, of a wave which is propagated under sort of a one-dimensional ice sheet. Okay, so here there is no variations in the y direction, so it's really one-dimensional wave propagation into the ice sheets, and then just repeatedly break up that ice sheet. So here we modeled the ice sheet using like some simple elastic plate model, and we also added a bit of viscous damping to make sure there is some enough attenuation happening. And the idea here is that given a forcing wave field, so like amplitude, period, and the phase of the waves, we get the corresponding strain field throughout the ice cover. And then based on the strain field, if it's strong enough, then we can break the ice accordingly. So don't worry too much about this diagram here, but that's kind of an overview of the simulation we've done. The idea is that we started with an infinite ice sheet, and we just repeatedly broke it apart by sending waves again and again and again until it stopped breaking up. And we just, introduce a critical strain here to determine when it breaks. And we just assume as well that there is just each flow can break only once at each step of the simulation. And what we found is definitely not a power law at all. We have this relationship where there's a clear mode in the distribution. And that is very consistent for many, many different parameters that we used to model the system. Consistently, we have this relationship, and it seems that the log normal distribution instead gives a very, very good fit. And this relationship seems to hold for a broad range of different parameters. So log normal power law, what is it? Or is it maybe another distribution as well? So the power law could be explained at least by some simple fractal self-similar, like repeated fragmentation process I mentioned earlier. What about the log normal? Can it be explaining like that? And it turns out it can, and it's not new. There's this Kolmogorov fragmentation theory, which was proposed in the 1940s, and it had nothing to do with sea ice at the time. And as far as we know, it's never been really discussed in the context of sea ice breakup as well. And so the way it works is fairly simple. You start with just one flow of size D0, but instead of breaking it exactly in the middle, you just break it at a random point this time. But the point at which you break it randomly is not necessarily based on a uniform distribution. It can have some other type of distribution governing it. And then you just repeat. You keep doing that and that and that. And what you obtain after a while is this kind of multiplicative fragmentation process here. And as it turned out, in the limit, this follows a log normal distribution. And you can show that theoretically fairly straightforwardly, actually. So it is nice because now we have a way to also explain that the log normal could emerge from this repeated fragmentation process. So we've also looked at some data. So yeah, I'm running a bit late here. So we just managed to get our hand on one data set so far, but we are definitely want to look at more. And what we found by looking at this one data set is that instead of looking at the cumulative distribution on a log-log scale, like many others have done before, if you look at the actual probability density function, then it seems like there is a mode as well here in this data set anyway. And the log normal was actually better than other distribution we looked at as well. So one issue with the log normal, though, is that it seems to overestimate the tail of the distribution. It captures well the mode, but it seems to overestimate the tail. So it may not be the whole story here. All right. So just to finish it here. So we have shown that the log normal should at least be considered as a potential alternative to the power law in representing the flow size distribution. And it seems to make sense as well in terms of repeated fragmentation of the ice cover. So it emerges from the simulations we've done and this random fragmentation process, and also looking at data sets. So things that we also don't know is the log normal, does it hold for other data sets on larger scales of flows, and of course, how to actually parameterize that in large-scale model will be another issues. So yeah, I think that's all for me. We got a couple of papers which are not published yet, but you can still read them both online if you want. So thanks.